All right. This is Batteries and EMF, the second section in the first unit of Physics C notes. Okay. We're going to start talking a little bit more about circuits and what they are. Okay. So let's start by talking about electromotive force. You're going to hear it shorthanded a lot as EMF. Okay. The symbol is this backwards 3, which we call epsilon. Okay. The units for this are volts. Okay. Which are shorthanded as a V. What does EMF do? It gives charges energy. Okay. And it pushes charges around the circuit. Okay. So if you say 3 volts equals 3 joules, so when it says that something has 3 volts, you're actually saying that 3 joules are held by each coulomb of charge. Okay, and we don't usually say coulomb of charge every single time. I'm just trying to make sure that that you understand that. Okay, here's our example. Okay, we have a pizza shop. Okay, let's say that we have a pizza shop, and he is delivering pizzas, and this customer is ordering tons of pizzas, infinitely many pizzas. Okay, and the pizza shop has to derive a new way to get pizzas to the customer because the customer is ordering so many pizzas. So what the pizza shop decides to do is they are going to get all of their delivery cars bumper to bumper in the road. They're going to shut down all these roads, and they're going to get their cars bumper to bumper, and they're going to basically form like almost a sort of conga line to get to the customer's house. And they're going to go like I said, they're going bumper to bumper. So they're super, super close. They're going to make this kind of big loop. Okay. And I'm going to draw arrow points so that you can denote, so that we can see, hey, they're going this way, right? Okay. Okay. So what they're doing is they're at the pizza shop, and they're going to go and go and go and go to the customer's house. What happens is every time they pass the pizza shop, they're going to roll down their window. We're going to throw pizzas into their car, and then they're going to go, and then they're going to pass by the customer's house without stopping. They're just going to throw the pizzas on their porch. Okay. So let's suppose that there's a ton of delivery cars, end to end to end to end, going by the customer's house. Okay. So they're all going end to end, right? So let's say that every time they come by the pizza shop, they are getting 7 pizzas from us, and then we are getting 10 cars to pass the pizza shop every second. So they're going really, really fast. Okay. Okay. If the cars are end to end, bumper to bumper, right? They're basically attached at the bumper, right? Then how many cars pass the customer's house every second? Well, if 10 are passing the pizza shop every second, 10 should be passing the customer's house every second as well. Okay. How many pizzas did each car give to the customer? Well, we are giving them 7 pizzas, and they should not be returning with any pizza. So if we give them 7 pizzas, they should be giving all 7 to the customer. So each car is giving 7 pizzas to the customer every time they pass by. How many pizzas are we giving out every second? Well, if we're giving every car 7 pizzas and 10 cars are passing every second, then we are actually giving out 70 pizzas a second. And ideally, the customer should also be receiving 70 pizzas a second. Because again, if we should be giving out at the same rate that we're giving, right? I don't want anybody returning with any pizzas, okay? Okay, the pizzas in this analogy represent the energy given to the charges, right? The cars are the charges, the pizzas are the energy, okay? Energy given to charges by battery, okay? Charges are given to resistor. To resistor, okay? Okay, and like I said, the cars represent the charges, okay? That's what goes around the circuit. Okay. Oh, and they deliver energy. I should also say that too. And deliver energy. Okay. Okay. The cars per second, that represents the charges moving per second. And you should know charges per second is current. Okay. You should know that pizzas per car is the amount of energy that each car carries, which is voltage. Energy each car carries is voltage. Okay. And finally, the pizzas per second. Okay, that's, well, we already said pizza represents energy. Energy per second. If you're thinking back to physics 1, we did do energy per second. It was called power. Okay, so it's the energy per second, which is power. Okay. Okay. Um, Now, you're going to hear these words: EMF, electric potential, potential difference, voltage, voltage drop. These are all words that almost sort of get used interchangeably, but they do have different definitions. They kind of get thrown around a lot as being the same thing, but they all have different definitions, and you do need to know their definitions. They all have the same units, though. It's volts. Okay? The unit symbol is a V. 1 volt is 1 joule per coulomb. Okay. EMF is the amount. Wait, so what do some of these words mean? Okay. Well, EMF is the amount of energy that each coulomb of charge receives. Okay. Each coulomb of charge is going to receive some amount of energy. That's EMF. Voltage drop is the amount of energy that each coulomb, okay, gives away. Okay. And electric potential is the amount of energy that each coulomb of charge possesses. Okay, you can kind of see, receiving, giving away, holding, right? Okay. Okay. On the next page, we talk about Joule's law, which is power. Okay. In physics 1, you did go over power. It was more so about energy, right? It was more so about like kinetic energy, potential energy, stuff like that. There is still power in physics C. Okay. This is a basic equation is power equals voltage, okay, times current. Okay. And when you do that, you're actually going to see that voltage is energy per charge. Okay. And if you multiply that by current, which is charges per time, okay, then you end up seeing that, based on math, charge and charge cancels out. You get energy per time, which is more close to our physics 1 definition. Okay. Okay. The general form for it is P equals IV. Okay. You're going to see that a lot. It's very important to know that one. Okay. Resistance is the ability or the property of an object that makes it difficult for charges to flow through. Okay. Makes it difficult for charges to flow through. Okay. The symbol is a capital R, and the units are ohms. Okay. And that's supposed to be a capital omega, by the way. I'm not very good at drawing them. Okay. But that's okay. Okay. Basic equation that relates current, voltage, and resistance. This is probably the most popular E&M equation. Okay, you're going to see it one of two ways. You'll either see I equals V over R, or you'll see it as V equals I times R. Okay, and so I being current, okay, V being voltage, okay, and R being resistance. Okay, so you can solve it pretty easily there. You're probably more familiar with V equals IR. That's kind of a little bit, or V equals IR. That's a more popular one. Okay, V is the voltage or like the push. Okay, you can think of this as like an analogy, like when you're at school, right? Okay, I is the flow, and R is the resistance. Okay. My analogy is like when you're in school, right? The students at school are the charges, they're the flow, they're the current. Okay. And the APs are telling you to go to class, they're the push, right? And then the resistors are like your classrooms. That's where we want the charges to go, and that where we want them to expend their energy, right? Our goal is that you are spending your energy working in our classrooms, right? Learning, okay, and then you go back home, you recharge, you come back to school, you do it all over again, right? Okay. Now we can actually develop a new equation for power. Okay, there's two new power equations we can use. Oh, sorry, we can actually develop two different equations for power. Okay, if you know that P is equal to I times V, okay, and you know that where is a blue? Let's use this one. Okay, and you take this expression, okay, and you substitute it for the I in here, then you will get P equals V over R times V, which will actually give you P equals V squared over R. Okay, that's one. Now, if you use the other one, if you still use P equals IV, okay, but this time you use this expression and substitute it in for the V, then you get P equals I times R, which gives you P equals I squared times R. And it says to name which one is better. I don't really think either one is better, in my opinion. I think that both of these are good. You just have to know what you're working with. I think technically this one is better just because there's no current involved in it. But just because there's no current involved in it whatsoever, two of the three power equations we looked at have current involved. This one does not. Okay. Okay. What does it mean for an object to be ohmic? What does it mean for it to be non-ohmic? So there's a difference between ohmic and non-ohmic. Okay. Ohmic means it follows Ohm's law. Okay. That means that V and I, voltage and current, are directly proportional. Okay. Non-ohmic, okay, means V and I have a nonlinear relationship. Okay. So you'll see that in some cases there are certain resistors that are non-ohmic. They do not obey Ohm's law. Okay. And the most popular one is a light bulb. Okay. And so if you were to look at at a graph of different different resistors, right, you might see that if you have a low resistance resistor, okay, then your graph might look something kind of like this. Okay, that's a low resistance. Okay, if you have a high resistance resistor, okay, it's probably going to look something like this. Okay, okay. If you have a light bulb, it's probably going to look something like this. And this is going to be where it gets unusual, right? Okay, it's probably going to be curved like that. Okay, and then finally, if you have something like an LED, it's probably going to look something like this. Oh, I completely missed the point that I drew for it, but that's fine. Okay. That's going to be something like an LED. So notice that these ones that are curved, they don't have direct proportional relationships. They are not ohmic, okay, or non-ohmic, okay? So what gives a light bulb its brightness, okay? What quantity gives the light bulb its brightness? Most people think energy, right? Well, and you're technically right. It's not about the amount of energy that's delivered, it's about how fast it's being delivered. And that would be power, okay? This is the light emitted every second. Say, sorry, light energy. Okay. The light energy emitted every second. Okay. Now, when we look at ammeters and voltmeters, okay, it's very important to note that they need to be hooked up in certain ways. When you did the Ohm's Law lab, okay, you saw that an ammeter needed to be integrated into the circuit, whereas a voltmeter was a lot easier to handle because it didn't need to be integrated into it. So ammeters, which are denoted with an A and a circle, are in series. Okay. They go directly before or after what you want to measure. Okay. You integrate them into the circuit. It has to be a part of the circuit. Okay. Now, voltmeters are a little bit easier to use because you don't really need to necessarily integrate them into the circuit. You can kind of, like, if you remember the Ohm's Law lab, you can kind of just like put the leads on where it needs to go. Okay. But this would go in what we call parallel. Okay. If something's in series, that means it's basically integrated into the circuit. In parallel, you don't really have to. It's part of the circuit, but it's not like, baked into it, right? Okay. If it's in parallel, it needs to be connected to both ends, okay, of what we want V across. Okay. So you would have to, when you did it in the lab, you connected it to both ends of the resistor, and you saw, oh, this is the voltage across the resistor. Great, good job. Okay. All right. Okay, Mad Lib's example. This is a pretty fun one. We got a circuit to the right, or it's just to the right, it's to the left actually. It consists of a battery and two resistors. Draw an ammeter in the circuit that would measure the current in the circuit. Draw a voltmeter in the circuit that would measure the voltage drop on B. Okay, I encourage you to try this on your own before you actually watch me do it. Okay, but I'm going to start out by doing the ammeter and the voltmeter. Okay, you can put the ammeter on any wire, but it has to be integrated into the circuit. So I'm going to put the ammeter right here, okay? And that's perfectly fine. You could have put it there, you could have put it here, you could have put it here, here, or even between the resistors. That's fine too, okay? Doesn't matter. Now the voltmeter, it needs to be connected to the start and end of where you're trying to measure from. So I would put it maybe right here, okay? That's your voltmeter, okay? That's all you got to do. You can add extra wires to it, right? Because obviously your voltmeter is going to be, you're touching the leads to it, right? Okay. Okay. In the Mad Libs example, again, like I said, I encourage you to try this on your own first, but let's go through it really quickly. Okay. The EMF of the battery is 12 volts. Volts. Okay. And you can see that from up here. It just says 12 volts. As charges pass through the battery, each coulomb of charge gains 12 joules of electrical energy. Okay, so every single time a charge passes the battery is giving it 12 joules of electrical energy, which it will then go use on the resistors. Okay, the voltmeter measures 8 volts of potential difference. I'm going to shorten it as pot diff. Okay, potential difference, it's voltage, right? This means that as charges pass through resistor B, each coulomb of charge, okay, loses 8 joules of electrical energy. Okay. The ammeter measures 2 amperes. or amps, let's find 2, of current in the circuit. This means that at any point, 2 coulombs of charge pass every second. Okay? The resistance of B is 4 ohms. Okay? This means it takes 4 more volts of potential difference to increase the current in the resistor by 1 ampere. Okay? The power delivered by the battery is 24 watts. Okay? Where did there it is. Okay? 24 watts. This means that the battery delivers 24 joules of electrical energy to the charges every second. Okay? All right. That is batteries and EMF. Okay? All right.